opportunity. So today I will talk about relational supersymmetry and matter interaction supergeometric framework. So what I mean with this to start, first of all, relational, so supersymmetry, and also the matter interaction supergeometric framework that I will present. There will be a first part of the talk on relational supersymmetry, say, and a second part on matter interaction supergeometric framework. What I mean with relational, that the physics, so the physical content of a theory is given by the relations instantiated between the degrees of freedom of a theory that might be, as we will see in this case, field theoretical degrees of freedom. So, physics, relations between degrees of freedom. Without any background non-dynamical structure. So this is what is intended with the relationality, and we can take relationality to be the paradigmatic feature of general-relativistic gauge field theory. And it allows to describe physics via physical observable, so gauge-invariant observable in particular. And this can be achieved in different ways. One tool, systematic tool, geometric tool to make things relational in a manifest way, so gauge and automatically gauge invariant, is a tool that is called the dressing field method of symmetry reduction. So I will review this in the talk. This is just to give you an overview of what I will talk about during this talk. So why relational? Because it's physics, because it's physical, and supersymmetry. We may ask why supersymmetry, okay? And under a phenomenological perspective, one may think of the existence of supersymmetry and thinking that it will be found at a certain point, or maybe not. But the point today is that independently of this, first of all, if you think of supersymmetric physics and so of supersymmetry to be something that has to be considered in principle under a theoretical perspective, it is still not completely clear, not only in relation with its connection with string theory and superstring theory, but by itself at classical and quantum level there are still subtleties and things that have to be understood under a theoretical perspective. And we will see that this can be done via the dressing field method, achieving in this way the physical content of a supersymmetric field theory, and therefore what we have called in collaboration with Jean-François relational supersymmetry. Then matter interaction supergeometric framework. So why so? Because this is a framework. It's based on supergeometry. So and it doesn't. We know that in standard supersymmetry there are some requirements. We have to have a matching between the bosonic and the fermionic degrees of freedom. And if we just think of supergeometry as a tool where to develop physics, we don't need this matching of these degrees of freedom. It's just using supergeometry, we will see how, in a manifestly relational way. So it will be relational matter interaction supergeometric framework, to just describe matter fields, so fermionic matter fields, and bosonic gauge fields in a unified way, using supergeometry by means of a superconnection. So this will stand independently of the empirical successor of supersymmetry, and it remains agnostic as a framework on the existence of supersymmetry. And we see both of these framework anyway will be relational, and we will see how to make physics, and in particular in this case supersymmetry, standard and non-relational. How we will do this? Well, first of all, we will see that in a first part of the talk, I will show that some conditions that are commonly referred to gauge fixing condition in supersymmetric field theory they are commonly referred to gauge fixing condition on the Rarita-Schwinger field that is the key ingredient of supersymmetry. So it's a spinor vector field, we will see in detail. It is gauge fixing in such a way to get to the number of shell and the non-shell degrees of freedom that one want to achieve, thinking of standard supersymmetry, therefore of the matching between bosonic and fermionic degrees of freedom. Actually, these gauge fixing constraint and procedure are actually instances of the dressing field method of symmetry reduction, and in particular they are self-dressing of the gravitino field, and therefore the gravitino itself, sorry, not the gravitino, the Rarita-Schwinger field for rigid supersymmetry, and the gravitino in the case of supergravity. We did develop both with John and Francois. I will also give you now some references, but today I will focus on the case of the Rarita-Schwinger field, which is easier and immediate to see which is the thing. But the point is that it will be a relational variable. So Rarita-Schwinger field is a relational self-dressed field. And so for Rarita-Schwinger, for the gravitino, in the case of supergravity, and I will leave in mind the details. And then, in the second part of the talk, I will describe this matter interaction supergeometric framework, and in which we will see this is also related to what has been called unconventional supersymmetry in some literature, developed by Alvarez, Valenzuela, and Zanelli. They consider a simple toy model in 3 dimensions, in which they tried to unify gauge bosons and fermionic matter fields in a single superconnection, so therefore just using supergeometry. And they developed a model that is called now AVZ model, and it is an analog model used to describe, they show that it is able to describe graphene in some particular points at the DR points. So they were interested in this analog modeling via supergeometry. And then they tried to extend this unconventional supersymmetry framework to higher dimensions, not only to 3, but to 4 and so on. And they didn't manage to, but we showed by means of a fully fledged matter interaction supergeometric framework how to do this and how this come out to be naturally relational. In particular, in this framework, we have we see a super connection whose, let's say, A, whose odd part is a spinor 1/4 field psi. So, and to develop unconventional supersymmetry in the AVZ model, but also, as we will see in the matter interaction supergeometric framework, we have to consider an ansatz in which psi is proportional to gamma chi, where gamma is the gamma matrix 1 form, so it's gamma mu x mu. And this was called the matter ansatz in this USUSI unconventional supersymmetry literature. These actually result to be, it was considered in some other literature a gauge fixing. We have shown that actually is again addressing, implementing the addressing field method. The object that appears in the super connection, now expressed in terms of the spin 1/2 field, is addressed object, is a relational variable, self-addressed again. And so we see that relationality is again core of this unconventional supersymmetry, matter interaction supergeometric unification. And by doing so in a clear, neat geometric way, you also manage to extend what was previously developed in the literature more or less with the same spirit, but also to extend it to higher dimension to correct something that we're presenting in the literature. So let me give you some references regarding the dressing field method essentially all the works done in the last 10 years, I would say, by Berezin. More abstract, mathematical, and also more physical and also philosophical. So conceptual and technical, you can dig into this literature. Then I will give you the archive idea of the paper. So then we have the application of the dressing field method to general-relativistic gauge field theory. So to a broad spectrum of theories, in fact, in this paper, 247-0443 by Giorgia François and me. And regarding those two topics that we will touch today, I will give you the new paper, which is 2503, 1977, which is actually a review paper with some new part regarding the matter interaction supergeometric framework of two other papers on supersymmetry. And on unconventional supersymmetry. So MISU is a dressing field method is 412. Okay. So we can start, I think, before going into the details of, I would want to show you how technically those gauge fixing that are implemented in the supersymmetric field theory literature, if you go there, you will see immediately at least one of them implemented. There are actually instances of the dressing field method. To do so, we start from introducing the basic of gauge field theory, starting from the kinematics and then giving you the dynamics of a theory. So just to have a common language, and then we will see the explicit examples. So regarding the kinematics, the basics of gauge field theory. Regarding the kinematics, we say that the theory is developed, lives, if you want, over some region U of M. In this case, we will consider 4 space-time dimensions. So M in general is an n-dimensional manifold. We will focus, especially for simplicity, on the equal 4, but anyway. And it is based, gauge field theory, on some gauge group H, to which it is associated the algebra H. Then we define the object that we have in gauge field theory, so the fields that populate gauge field theory, that are the gauge potential, or connection one form A. Let me write also this time, either in compact notation or explicitly, which is a one form. And then we have matter fields. Then we know that to introduce what we typically do in gauge field theory is to introduce some minimal coupling procedure, and this is done via the introduction of a covariant derivative of the matter field. So we introduce the covariant derivative defined as d phi plus, and then some representation rho a phi. This is just we write it formally. Then, of course, when seeing the explicit application to supersymmetry, we write the covariant derivative explicitly for the representation that we will consider. So we can say matter field say forms UV with V a representation space via rho with mass from H to G and B, and rho star mapping from H to G and the algebra G and B. This is just formally, but those are the ingredients that we use to build the theory. And correspondingly, we can write the field strength, the curvature for F, for A, that is F, so the field strength F, it is dA plus 1/2 AA, and it is a two-form, and we know that it obeys the Bianchi identities dF with the derivative taken with respect to the connection A equal to 0. So those objects are subject to some gauge transformations given by the gauge group associated to what would be called in Vandal geometry the structure group H, on which the gauge field theory is based. So we have a gauge group H. Let me denote it in this way. To H, the other one is the rigid, say the structure group. Multiple H if you want. So H in this way is the gauge group, and it is defined as the group of elements gamma and beta, mapping from mu to H, such that beta transforms in this way under gamma. And correspondingly, we can write in the infinitesimal level, we can write the Lie algebra associated with the gauge group, so Lie H, whose elements are the parameters along which we compute the linear infinitesimal gauge transformation when we do theoretical physics. Many times we just deal actually with the infinitesimal transformations in high energy physics. Right? So lambda prime and to H delta lambda prime is lambda prime lambda. And as I was mentioning before, the objects that we have in our theory are subject to the action of the gauge group, and therefore we can write their gauge transformations. For the connection, formally, we write that the gauge transform connection is gamma minus 1 A gamma plus an homogeneous gamma minus 1 A gamma, and phi, the matter field transform as rho gamma minus 1 phi. If we want now, those are the finite gauge transformations, and one would actually want to deal with them for having a finite, for having control of the finite transformation of a theory. But sometimes also when we develop, when we study invariance in a theory, we would have a finite one. But then sometimes what typically happens for convenience is that we focus on the infinitesimal transformation, therefore we require invariance. In particular, this occurs in supersymmetric field theories. We require invariance at first order, and we consider the infinitesimal gauge transformations. So at the infinitesimal level, what we write is delta lambda A is the covariant derivative of lambda, and therefore in general is the lambda plus adjoint representation of A lambda, and delta lambda phi is minus rho star lambda phi. Same we can write then for the curvature. So for the curvature we have F gamma is gamma minus 1 F gamma, and the covariant derivative of phi transforms as d phi gamma plus rho star A gamma phi gamma, which is rho gamma minus 1 d phi. So this is regarding the kinematics. Then, with this set of fields and their field strengths, we may write we may focus on the dynamics, so write some Lagrangian, having in mind Lagrangian dynamics. So once we have this kinematical setup, we write the dynamics in terms of a Lagrangian, which is the function of the field variables that we have at our disposal in our field space. And so, and we can write it as a Lagrangian density if you want. And what we require, typically, is quasi-invariance of the Lagrangian under gauge transformation. Quasi-invariance meaning invariance up to boundary terms. That is, if we now take the transformed Lagrangian, the gauge transformed Lagrangian, therefore written as a functional expression of the gauge transformed field, we require that it is the original Lagrangian plus a boundary term, given in terms of the of the field of the theory and of the gauge parameter gamma. And this quasi-invariance of the Lagrangian is such that the field equation, let me write them formally in this way, just the formal expression of the field equation. Therefore, the field equation function of the fields equals 0 remain H covariant. Now, what is important at this level is to remind that sometimes, so these kinematics and these dynamics are nice, we know how to deal with this, but then when we have to implement these studies of theory in a technical way, sometimes it is hard to deal with field variables. And so for technical reasons, and sometimes also driven in a sense by physical reason, we will see that this is actually slightly incorrect and we can do better than this. But what we try to do is to do some gauge fixing. Some gauge fixing to simplify, to constrain the field variables that we have and simplify the calculation and somehow the field theoretical degrees of freedom that we have to deal with. And so we consider, say, the set of field A phi that we have in a gauge field theory to be restricted to satisfy some gauge fixing constraint. Let me call it formally a constraint on the transformed variables. Formally, I indicated the gauge fixing constraint this way. And this, first of all, is not a gauge fixing, is never invariant. Let me first of all notice this. And then what does this correspond to if we think of field space? So this is the set of field, and we may think of field space as a bundle and see under a geometrical point of view to what this operation corresponds. So if we take, let me just do this schematically, and then we will see technically how what I'm mentioning now is implemented in supersymmetric field theory. We have the space of our field, the gauge group acting on them. Each point of the gauge group is a parameter gamma, and the moduli space of field space. Here we have the orbits. This is say the point A phi. This is the gauge transform point A gamma phi gamma. This is a region that we may consider a region U of the moduli space of phi. We have a projection, that's projection from phi to M. And then we have what is called a section of this bundle, so say is sigma. And when we do a gauge fixing, we just consider this gauge fixed slice, C, A gamma, phi gamma equals 0. So a gauge fixing results in the image of a section in field space. And so this, we can call this slice that we are considering a gauge fixing constraint. We will see that this is conceptually, mathematically, this is provided in some details in a paper by Philip Berezin and Jordan François. The difference between a gauge fixing and a dressing field method. But so this is what we have to keep in mind for gauge fixing. We will see in a while the addressing, how we can take these constraints, actually solve them explicitly, extracting an addressing field that has to transform in a certain way, and it's not an element of the gauge group, in such a way to obtain to manage to deal with what they are called, if you want, the equivalence classes in physics sometimes. So what happens is that addressing, as we will see in a while, is correspond to doing a projection of phi on M, and therefore to have access to points, say, A, phi. So this is just to mention a key difference that we will see, that we will now see. So, dressing field method that we now introduce, so we understand somehow that it has to be different from gauge fixing, and let's see on what it consists. We have to consider a subgroup of H, and therefore as a group of the gauge group. And then we call a K-dressing field a map. It is an object that is not, first of all, let me start from what it is not, and then I will tell you what it is. So it is not an element of K, of H, it is not an element of the gauge group, but it's a field that has to transform under K transformation, K gauge transformation. It has to transform as K minus 1 U for K in K. If we manage to find, and possibly it has to be not introduced from the outside in a theory, but it has to somehow be extracted from the field, from the field theoretical degrees of freedom that we have at our disposal in a theory. We will see how this can be done explicitly. So if we manage to extract a dressing field that transforms in this way under the gauge transformation that we are going to reduce, we are in fact reducing the symmetry, in which sense that we are building dressed objects that are gauge-invariant variables. They are dressed fields. Say AU by U. And under a kinematical perspective, with these dressed variables, we can write, so how do they look like kinematically? We have what is called a rule of thumb of the dressing field. So to build the dressing field, the dressed fields, once we have extracted a dressing field, we just look at the gauge transformation of the fields, and we replace formally the gauge parameter with the dressing field, reminding that the dressing field is not a gauge parameter still. So if we write now the dressed object, they will be U minus 1. They are defined as U minus 1 AU plus U minus 1 DU, and phi U is defined as U minus 1 phi, and they are K invariant. And same for the curvatures, of course, we write FU, which is U minus 1 FU, and du phi U, which will be d phi U AU by U. And once we have the dressed field, so we managed to build in this way gauge-invariant variables, physical observables if you want, in a sense they are related to this notion of gauge-invariance field theoretical variables. And then we can look at the dynamics and write either just write a Lagrangian in terms of this object or start from the bare one, write it in terms of the dressed object, and we will simply obtain. So for the dynamics, we will have the Lagrangian that is a functional expression, now is the dressed Lagrangian, so it's a functional expression of the dressed fields. And again, by the rule of thumb of the dressing field method, we can have a look at how it is considered to be quasi-invariant and the gauge transformation. We replace the gauge transformation rule for the Lagrangian, so substituting the parameter with the dressing field, and again we see that we have that is, if we unfold the dressing in terms of the bare plus the other contribution, we will have an A phi plus a boundary term written in terms of A phi and the dressing field. And the field equation for this series, so functional AU phi U, have now the same functional expression of the initial field equation. The functional expression is the same, but of course if we unfold them in terms of the bare variables, also being the fact that the dressing sometimes, as we will see, can be non-local, is non-trivial to unfold all the contribution. But formally, they have the same functional expression as the E of A phi that we have written before. Another important thing to say about the dressing field method, just so this is just an entry for the dressing field method, that is what we need to understand what will come in a while, is that we can have residual symmetries. Before mentioning this, let me just say that what is most relevant at this point is that the dressing field can be a field-dependent dressing field, meaning that it is built with some field theoretical variables that we have at our disposal. So is A phi. It is built with the field theoretical degrees of freedom of our theory, and it allows in a natural way a relational interpretation, meaning that it allows to access those gauge-invariant, physical observable, relational variables, if you want, those relations among the bare degrees of freedom that we have constructed via the dressing. So the dressing field method is a mathematical tool, a systematic mathematical tool that allows to do this, okay? When we reduce the symmetry and we build these invariant objects, there might be some residual symmetries. And there can be, we make a distinction between residual symmetries of the first kind and of the second kind. What we will, today we will see something with residual symmetry of the first kind. And this occurs when the symmetry that we reduce is not the whole group H, but it's just a subgroup of it. And so this is the case when H in particular, they are meaningful, this is the residual symmetry of the first kind, when K is a normal subgroup of H, and therefore R over K is a group itself. And for instance, we have, how do we manage to do something with this residual symmetry to get to the residual symmetry of the dressed field? Naturally, we know the bare variables, their transformations. Then, if we know the way in which the dressing field transforms, we can see how the dressed variable transforms. And so, for instance, we will see examples in which U transforms in this way, in J, and this is a typical example that is considered that we make, and by means of this, you can then reconstruct how the dressed field transform under this residual symmetry of the first kind. Residual symmetry of the second kind encode say an ambiguity. Diamo stato in a sense ambiguity in choice of dressing. Because it might be that some symmetry can be reduced by extracting the same amount of degrees of freedom but via different dressing in a theory. And so when this ambiguity is there, it is encoded in this residual symmetry of the second kind, which at best it can be some discrete group, some group of transformation. So, but anyway, today we will not focus on this aspect, but we will have some residual transformation of the first kind, in particular in the matter interaction supergeometric framework. Okay, so given what we have just seen for the dressing, and the fact that the first thing that I said is that the dressing field is not an element of the gauge group, let me also, in this scheme, again, just for giving you some image of what is happening conceptually, is the fact that so a dressing via U can be thought of as phi, as doing a projection from phi to the moduli space, and so to equivalence classes A phi or AU phi U, if you prefer. And it is not therefore a gauge fixing. So we can now see, in the case of supersymmetry, and in particular in the case of the Rarita-Schwinger field, how some conditions that in the literature are key because they allow you to reproduce the number of off-shell degrees of freedom that you may want to start with to then build the theory and study how it behaves on shell. But then the degrees of freedom that you start with, they are gauge fixed degrees of freedom, they are said to be so. And actually that is precisely an instance of the dressing field method. And this occurs frequently actually in the literature. So let's see this example. So the Rarita-Schwinger field is a spinor vector psi alpha mu are space-time indices. Let me focus in the equal for space-time dimension and equal one amount for supersymmetry for simplicity. Then it can extend into higher dimensional theories and unextended models. But let's focus on this. So alpha is a spinor index. It's a 4-component spinor. And those are the components of the Rarita-Schwinger one-fold field. So psi mu delta mu. And let me observe that this object has inside a spin, it's irreducible, a spin 3/2, a spin 1/2, and a spin 1/2. Again, in the literature, sometimes it is called by default a spin 3/2, whatever is meant with this. But actually, the components it contains, there are 16, 4 times 4 degrees of freedom, if you want to count these degrees of freedom in this way. And they are therefore 8 for 4 of 2 spin 1/2 field and a spin 1/2 divergence-free traceless field. So this field is used to build what is called the Rarita-Schwinger Lagrangian. That is, if you want in supergravity, this term coupled with the Einstein-Hilbert term is what gives you supergravity. So everything starts from here anyway, in the supersymmetry sense. The Rarita-Schwinger Lagrangian is psi bar gamma 5 gamma big psi, where gamma is gamma mu dx mu, gamma 1 form. These are written in forms. If you prefer, rather than differential form, to see it in components, it is epsilon mu rho sigma, the Levi-Civita tensor, psi bar mu, gamma 5, gamma mu, 0 psi sigma, with your gamma matrices and the gamma 5 matrix. They are Majorana spinor, the Rarita-Schwinger field is from Majorana spinor. And what is important at this stage is to see how it transforms under supersymmetric transformations. So this Lagrangian is quasi-invariant, meaning it transforms with a boundary term under supersymmetric transformation that psi goes into psi epsilon, it is psi plus the epsilon. Epsilon is a spin 1/2 parameter, is the spin field of supersymmetry, is the spin 1/2 field. If you want in components, this is psi epsilon mu is psi mu plus the mu epsilon, and it is so epsilon is epsilon x in 1/2 parameter, and we have in this case it is an additive abelian symmetry, meaning that if we take epsilon prime, this is equal epsilon, and it can be checked that psi epsilon prime, so if we double transform psi, we get psi plus d. Let me be shorten this, but just this is important anyway technically. So it is additive abelian symmetry. Now we have these supersymmetric transformations, and so we have the field, the Lagrangian, the supersymmetric transformation leaving the Lagrangian invariant, and what it is done in the literature is some gauge fixing. So let me write it here just to mention to you those gauge fixing, which are either these or these. This is a gamma tracelessness condition. This is a divergence free condition. They are called gauge fixing. They kill, quote unquote, 4 degrees of freedom in such a way, it is said, that we are left with 12 degrees of freedom of shell corresponding to a spin 3/2 field. First of all, to correct something that may occur in the supersymmetry literature, actually those 12 degrees of freedom are still at 3/2 plus 1/2. So it's not a spin 3/2, but it still encodes a 1/2 component. And it can be either the divergence or the gamma trace, depending on which gauge fixing, quote unquote, one imposes. And then they are typically, this is the one that is chosen because this is harder to get than to deal with and to possibly get in some other formalism from the Lagrangian. And anyway, they are implemented on the field, this is implemented on the field of shell, and then the dynamics is studied and the theory is developed. What I would want to show you today is that none of them is actually a gauge fixing, but it is a dressing via the dressing field method, so a specific thing that is another thing. And the Rarita-Schwinger field turns out to be a self-dressed field. Let me focus on this case. If then you're interested, we will see also the other example, but I don't think there will be time. So let's take this object and see that it is actually, that gauge fixing is not a gauge fixing, but it's a dressing. To do this, we have to extract a dressing field, and to do this, we can use some either irreducible or reducible representation. In this case, we use this reducible representation, decomposition, if you want. Psi alpha mu is rho alpha mu plus gamma mu chi, where rho is a 3/2 plus 1/2 component. It is as such gamma mu rho mu is equal to 0. while chi is the gamma trace part, and so in n dimension it is 1 over n gamma mu psi alpha mu. In 4 dimension this is 4. And so, first of all, we use this decomposition. We may then look at the way in which those two objects, rho and chi, in this decomposition transform under supersymmetric transformation. We just use the same decomposition on the transformed objects. So what we get is that chi transforms in this way, the epsilon, and rho mu transforms as rho mu minus 1 over n gamma mu the slash epsilon plus the mu epsilon, where the slash is gamma mu d mu. So these are the SUSY transformations of these components. This is 3/2 plus 1/2, and here is, if you want, 12 degrees of freedom, and this is a spin 1/2 field varying 4 degrees of freedom. And now we try to implement the dressing field method. How does it work? We ask, can we build an object in this way? We introduce a new variable that will be our dressed field, so psi u mu. We define it as psi mu plus d mu u. How so? Having in mind the rule of thumb for the dressing field method, in which we replace the parameter with the dressing field that is not a parameter, still we use this rule of thumb. This is what would be our dressed object, and we ask if it is possible to implement this condition on the dressed variable. What was before the gauge fixing condition. Now we actually ask this condition to hold for these dressed variables, and we see if it is possible to solve it explicitly for u. So we solve explicitly a gauge fixing condition. It is possible. What we get in this case is u psi is minus d slash minus 1 gamma mu psi mu, and so it is minus n d slash minus 1 chi. So this is the field. It is field dependent. It depends on chi. It is non-local. True. So we have extracted a non-local object in terms of the field theoretic variables that we have at our disposal. And now we shall ask, is this a gauge group element or it is a dressing field? So we checked how it transforms, if it transforms as a dressing field or not. If it was a gauge fixing, we would have, in the case we have super translation, so it's for supersymmetry, an additive abelian symmetry. So we would just have u psi epsilon is equal u psi epsilon equal u psi for gauge fixing. And we see that this is not the case, in fact, because if we check now the explicit transformation of this object, let me write you what it is. It is u psi epsilon. I define it as u of the transformed object. And so it is minus n d slash minus 1 chi epsilon. And so I take the transformation of chi that I've written before using the reducible decomposition of psi. And I get minus n d slash minus 1 chi plus 1 over n d slash epsilon. And this is minus n d slash minus 1 chi minus epsilon. And so we see that this is precisely u psi minus epsilon which is what we expect for the dressing field, the gauge transformation of the dressing field in the case of an additive abelian symmetry, that is a supersymmetry in this case. Okay. And so the dressed object, now we can replace the expression for the dressing field, and we get the dressed object, and we may check that essentially, or also in terms of the reducible representation, that the chi-u now is equal to 0, and rho u mu is equal to psi u mu. So the dressed field now correspond to having dressed the rho, the field rho into the reducible decomposition. And if you, why this? Because you can see it again by maybe just write this for clarity. This is, we take the transformation, we use the rule of thumb, it is this expression. We substitute the expression of u into it, and we get chi plus this slash minus 1 chi, and so you see that this is equal to 0. So by extracting this non-local dressing field, we have, let's say, killed the degrees of freedom corresponding to chi, so that the dressed chi is equal to 0, and the dressed field variable psi correspond to the dressed rho. So we are left with 12 degrees of freedom, and there are 12 self-dressed, so it's a relational, 12 relational degrees of freedom. Notice that these has been done at the price, say, of locality, and this is a signal, as it was shown in a paper by John and Francois. It was discussed in this way: when if to extract a dressing field explicitly, we get some non-locality in the dressing, it means that the symmetry that has been reduced can be, we can see it as a substantive symmetry, while in contrast to artificial, an artificial symmetry wouldn't cost locality if reduced via dressing. Okay, so this was to just show you how gauge fixing in the literature, in particular in supersymmetry literature, are actually instances of the dressing field method, and this is similar to what occurs for the axial gauge in QED. And the other condition, the mu psi mu equals 0, in analogous way, just using another reducible representation, the composition can be shown to be a dressing, and that is analogous to the Lorentz gauge in QED. So also those gauge fixing are actually instances of the dressing field method. And just, okay, I don't have time to go into the detail of the mapping interaction supergeometric framework, but just to mention what happens there. So for this was to tell you, okay, if we have to think of standard supersymmetric field theory now, and to do it, to clarify some aspect of it, which is in fact the case via the dressing field method, because several problems are actually dissolved or solved in this way by dealing with physical objects. So thinking of standard supersymmetry, we would want to build it in a relational, fully relational, manifesting invariant way, rather than with gauge fixing or other procedures. So thinking of supersymmetry in this way. And the second point is, okay, but let's not think of standard supersymmetry, but just of exploiting supergeometry as a tool to do some other unification, so not in the very spirit of supersymmetry, just of unify fermionic matter fields and bosonic gauge field in a single superconnection. And so having a geometric description of this first unification. This is possible by considering a superconnection, so which has even and odd components. In the odd components, we think of psi to be the odd component of this superconnection, and then we think of again trying to implement what was called the Matterhorn, it's in the literature, to implement some condition in such a way to end up, and actually we know that this will be done via the addressing in the literature that I show you. This is done via addressing, and it is shown that one can extract addressing field U in such a way that the odd component of this superconnection reduces by reducing supersymmetry. So those the transformation associated with this odd part of the connection, it reduces to gamma chi u, that is delta mu gamma u chi u, where gamma now is delta mu gamma mu, and therefore one may think of in general as writing it in terms of Ea mu, where Ea mu is the Filben component of the base manifold of this supergeometry. So two things before concluding, and I don't think I have time to show you the details of this approach, but just to give you what is this in spirit. We implement addressing, extracting addressing field in terms of rho. We use the same gamma trace decomposition, but we do a bit the inverse. So rho dressed will be 0, and we are left with the gamma trace part. So we reduce psi to chi dressed, gamma chi dressed, in such a way that we plug back into the superconnection these ansatz. So psi u will be equal to this, and it happens that if for a connection, typically we have like the Lorentz part, our thing, and this super part involving psi. Now we plug the results for the dressed field into psi, and what we get is q bar gamma chi. So we managed to introduce this dressed connection written in terms of the Filben of the base manifold into the superconnection, and we managed to give a unified description of bosonic gauge field and matter field represented by chi in these answers by using the supergeometry in which the whole psi is a part of the superconnection. And so this is a bit the spirit. To do so, you can, all of this relies on the choice of the super algebra we started with. The crucial point is that we cannot choose an algebra in which the generators Q, the anti-commutators of Q with Q goes in T space-time translation. This is the typical choice one does for standard supergravity. This is not the case for the matter interaction supergeometric framework. We have to think of a, let's say, super bundle geometric framework, anyway, of a supergeometric framework in which the base manifold is not given by the, would be in supergravity super Filben. It's just an even bosonic manifold, and the psi direction, the supersymmetry directions are in the fiber of this superbundle geometry. Anyway, they are internal direction. So in this way, and what we may think of use for developing such a framework, a good starting point are all super Lorentz. Supersymmetrization of not the Poincare algebra, so not in the super Poincare direction, but just of the supersymmetrization of the Lorentz algebra, so super Lorentz algebras. And this, it is possible, it was developed in 3 dimensions. It was not known how to develop it in 4 or extended dimension, but taking this kind of algebra as a starting point and then developing the dressed kinematics and the dynamics, it is possible to develop this matter interaction supergeometric framework in a complete way. And so our future effort will also go in this direction, so to higher dimensional models and extended models, which are slightly more involved, but still it's totally possible to just proceed with this tool, building relational variables and then relational dressed Lagrangian and so on. And those are so the super Lorentz algebras are those that we will use. And this also is connected to we will also investigate how this connects with non-commutative geometry and to tentatives of unifying gauge bosons and the X field in a single unified geometric framework. And so in this case, one would have fermionic matter field, gauge bosons and X fields, and then also gravity, taking into account the filament spanning the base manifold. So, but these are for future work. That's it.